This tiny robot weighs less than a tennis ball and can jump higher than anything in the world. In the competitive world of jumping robots, the previous record was 3.7 meters, enough to leap a single-story building. This jumper can reach 31 meters, higher than a 10-story building. It could jump all the way from the Statue of Liberty's feet up to eye level. But how does this jumping mechanism work? Well, the main structure consists of 4 pieces of carbon fiber bound together by elastic bands. Together, they create a spring that stores all the energy needed for the jump. At the top of the robot is a small motor. A string wrapped around the axle is connected to the bottom of the robot. So when the motor is turned on, it winds up the string, compressing the robot. And this stores energy in the carbon fiber and rubber bands. After about a minute and a half, the structure reaches maximum compression.
How do you know when to put it down?
Basically, once the bottom there sticks inward and it can stand up, right now it would roll over,
Right.
then you put it down.
Got it.
So, as soon as you can.
And at this point, a trigger releases the latch that's holding the string on the axle. So all the string unspools all at once, and the energy stored in the spring is released. The jumper goes from a standstill to over 100 kilometers an hour in only 9 milliseconds. That gives an acceleration of over 300 Gs. For years, engineered jumping was developed to mimic biological jumping, but with work multiplication, it gained an advantage. If you can generate a large burst of energy simply by running a motor for a long time, the power of the motor is no longer the limiting factor. The spring is. So you can focus on making the most powerful spring possible. This jumper has nearly maximized the achievable height with this spring. Assuming an infinitely light motor with infinite time to wind up, the highest possible jump with this compression spring is only around 19% higher than what they've achieved. If you want to incorporate air resistance and play with aerodynamics, another way to send the jumper higher is to make it 10 times isometrically larger, leading to a 15 to 20% higher jump.
So we're in kind of an intermediate scale where we still are getting hit by air drag, but it's not as bad as the Flea. If we went 10 times bigger, we could actually avoid air drag completely.
This works since if the jumper is scaled up 10 times on all sides, the cross-sectional area increases by 100, which increases the drag force, but the jumper's mass increases by 1,000, so it has way more inertia, meaning the drag force affects it less. The entire concept of work multiplication could bring robots to the next level. Currently, motors in robots have to be relatively small so they remain portable. But the simple principle of building up the energy from multiple turns of a motor over time would allow robots to store and then release huge amounts of energy, and set some world records in the process.